Are you ready to question everything you thought you knew about where European learning came from in the Middle Ages? Did you ever stop to think about the ancient roots of the very numbers you use every day, or the hidden stories behind the tools that helped explorers map the world? What if a huge part of the incredible scientific breakthroughs in medieval Europe, the ones taught in its first universities, actually arrived from another continent, another culture entirely? Number 6. The Great Translation Movement. Picture Europe in the early Middle Ages. The Western Roman Empire had crumbled centuries ago, leaving behind a continent fractured and largely focused on local survival. Knowledge, particularly the vast scientific and philosophical wisdom of ancient Greece, existed in scattered fragments, often in monasteries, painstakingly copied by hand. Much of it was simply lost, or remained untranslated into Latin, the scholarly language of the time. The intellectual light seemed dim across vast stretches of the land. Universities, as we recognize them, were still centuries away from their flourishing. Education largely revolved around theological studies, practical skills, and rudimentary literacy for the clergy. Meanwhile, a different kind of intellectual explosion was happening far to the east and south. The newly established Islamic Empire, stretching from Spain across North Africa, through the Middle East, and into Central Asia, embarked on an unprecedented quest for knowledge. Scholars, driven by curiosity and a cultural respect for learning, began to actively seek out, translate, and assimilate the wisdom of previous civilizations. This was not just about preservation. It was about understanding, critiquing, and building upon what came before. This enormous undertaking became known as the Great Translation Movement. The Abbasid Caliphate, centered in Baghdad, became a vibrant hub of this intellectual activity. In the 9th century, under the patronage of caliphs like Harun al-Rashid and his son al-Ma'mun, the city saw the establishment of institutions dedicated to this work. The House of Wisdom, or Beit al-Hikmah, was not just a library. It was a research center, an academy, and above all, a gigantic translation factory. Scholars from diverse backgrounds, Christians, Jews, and Muslims, worked side by side, translating Greek, Persian, and Indian texts into Arabic. Consider the sheer scale of this work. Imagine a single scholar, Hunayn ibn Ishaq, a Nestorian Christian, leading a team of translators. He was a master of Greek, Syriac, and Arabic. His method was incredibly meticulous. He would often translate a text from Greek into Syriac, then into Arabic, comparing multiple manuscripts to ensure accuracy, sometimes sending scribes on long journeys to find rarer, older versions. His team translated an immense volume of medical and philosophical works, including much of Galen and Hippocrates, the foundational texts of Western medicine. Without his efforts, many of these classical works might never have survived in a coherent form for future generations. The Arabic language itself became the new lingua franca of science and philosophy. This common tongue allowed scholars across the vast Islamic world, from Cordoba in Spain to Samarkand in Central Asia, to communicate, share discoveries, and collaborate. Think of it as a vast interconnected intellectual network where new ideas could spread rapidly. The translation movement was not a passive act of copying. Arabic scholars engaged with these texts, correcting errors, expanding on theories, and integrating them with their own observations and discoveries. They did not just absorb, they innovated. Centuries passed. As European states slowly re-emerged from the early medieval period and began to develop their own centers of learning, they looked south. Spain, particularly cities like Toledo, became a critical bridge. After the Christian reconquest of Toledo in 1085, the city became a unique melting pot of cultures, where Arabic, Hebrew, and Latin speakers coexisted. This created the perfect environment for a second wave of translations, but this time from Arabic into Latin. Think of Gerard of Cremona, an Italian scholar who arrived in Toledo in the 12th century, searching for Ptolemy's Almagest, a monumental astronomical text he knew existed in Arabic, but not in Latin. He ended up staying for decades, translating over 70 Arabic books into Latin. His output was staggering. Works by al-Khwarizmi on algebra, Ibn Sina's Canon of Medicine, al-Razi's medical encyclopedias, and many, many more. He was not alone. Michael Scott, another prominent translator, worked in Sicily and Toledo, bringing Aristotle's works on natural philosophy, along with the commentaries of Arab thinkers like Averroes, into the Latin West. The impact on European education was profound. Suddenly, European scholars, who had only fragmented or incomplete versions of ancient Greek texts, gained access to a vast treasure trove of knowledge. Euclid's Elements, the cornerstone of geometry, became available in full and accurate translations from Arabic versions. Ptolemy's Almagest, the definitive astronomical text, re-entered Europe, allowing for much more sophisticated celestial calculations. Galen and Hippocrates, the pillars of ancient medicine, were studied in comprehensive Arabic translations. This influx of texts fundamentally reshaped the curriculum of the burgeoning European universities. Students in Paris, Oxford, Bologna, and Salamanca began to pore over these newly translated Arabic works, provided the intellectual fuel for scholasticism, a method of learning that sought to reconcile classical philosophy with Christian theology. The rediscovery of Aristotle's complete works, preserved and often critically commented upon by Arabic scholars, transformed natural philosophy. It meant that a new logical framework for understanding the world was now at the disposal of European thinkers. Without the meticulous work of the Arabic translators and the vibrant intellectual environment they fostered, much of the classical heritage might have been lost forever, and the European Renaissance might have been delayed or taken a very different path. The knowledge flowed, like a fast river, from the Arabic world to the West, revitalizing its intellectual landscape. Number 5. The Hindu-Arabic numeral system and algebra. Imagine trying to do complex multiplication or division using Roman numerals. Think about it for a moment. How would you multiply cxy by xix? The system, based on letters like I, V, X, L, C, D, and M, was excellent for recording quantities, but incredibly cumbersome for actual calculation. It lacked a crucial element for advanced mathematics, a concept of place value and a symbol for nothing, for zero. European merchants, astronomers, and engineers in the early Middle Ages faced these limitations daily. Their calculations were often slow, prone to error, and limited in complexity, requiring elaborate abacuses or finger counting for anything beyond simple sums. Meanwhile, in the eastern parts of the world, a revolution in mathematics had been brewing. From India came a revolutionary system of 9 digits and a symbol for zero. This innovation avowed for a place value system, where the position of a digit determined its value, making large numbers easy to write and arithmetic operations incredibly efficient. This system traveled westward, adopted and refined by Arabic scholars. One of the most pivotal figures in this story was Muhammad ibn Musa al-Khwarizmi, a Persian scholar who lived in Baghdad in the 9th century. Associated with the House of Wisdom, al-Khwarizmi wrote 2 groundwork books that fundamentally changed mathematics. One was on the calculation with Hindu numerals. This book systematically introduced the Indian numeral system, including the concept of zero to the Arabic-speaking world. It explained how to perform arithmetic operations, addition, subtraction, multiplication, division, and extracting square roots using these new numbers. This was a clear, concise manual that quickly became a standard text. His second, even more influential work was the compendious book on calculation by completion and balancing, known in Arabic as al-Jabr wa al-Muqabala. It is from the title of this book that we get the word algebra. Al-Khwarizmi's algebra was not just a collection of problems, it was a systematic approach to solving linear and quadratic equations. He presented methods for dealing with various types of equations, using geometric proofs to justify his solutions. He showed how to manipulate equations by completion, adding terms to both sides to remove negative quantities, and balancing, subtracting equal terms from both sides to simplify. He also discussed topics like commercial transactions and inheritance, showing the practical applications of his new methods. The power of this new mathematics was immense. With the Hindu-Arabic numerals, calculations that previously took hours or were simply impossible became routine. Concept of zero as a placeholder, allowing for a positional notation, was truly joy. It made arithmetic a much more straightforward and elegant process. Algebra provided a powerful tool for solving problems that involved unknown quantities, applicable in everything from land measurement to astronomical calculations. Transmission of this mathematical revolution to Europe was gradual but profound. One of the most important figures in this process was Leonardo Fomai, an Italian mathematician from Pisa. In the early 13th century, Feidemann traveled extensively in North Africa and the Middle East, observing the mathematical practices of Arabic merchants and scholars. He recognized the immense superiority of the Hindu-Arabic system over Roman numerals. In 1202, he published his seminal work, Liber Abaci, Book of Calculation. In Liber Abaci, Feidemann explicitly introduced the Hindu-Arabic numeral system, including the zero, to European readers. He demonstrated its efficiency by working through numerous examples of commercial arithmetic, conversion of weights and measures, currency exchange, and other practical problems relevant to merchants. He showed how to add, subtract, multiply, and divide using these new digits. He also included chapters on algebra, drawing heavily from al-Khwarizmi's work, illustrating how to solve various types of equations. The initial adoption was slow. Some European scholars and traditional abbesses resisted the new system, finding the old ways more familiar. However, the sheer practical advantages of the Hindu-Arabic numerals soon became undeniable. Merchants quickly saw that calculations could be done faster and with fewer errors. Over the next few centuries, these numerals gradually replaced Roman numerals in commerce, record-keeping, and eventually in scientific and academic contexts. The impact on European science education was huge. The new numeral system simplified all forms of quantitative work. Astronomy, which required complex calculations of planetary positions, benefited immensely. Engineering and architecture, requiring precise measurements and structural calculations, became more feasible. Algebra provided a new language for expressing scientific laws and solving intricate problems in physics and optics. University curricula began to incorporate these new mathematical methods. Students learned the algorithm, which was a direct corruption of al-Khwarizmi's name, referring to the rules for arithmetic, using the Hindu-Arabic numerals. Mathematical faculties in universities started teaching these advanced techniques, equipping a new generation of scholars with powerful tools for scientific inquiry. The introduction of these numbers and the systematic approach to algebra laid the fundamental groundwork for all future mathematical and scientific advancements in Europe. Number 4. The astrolabe and advanced astronomy. Imagine looking up at the night sky in medieval Europe. You might know a few constellations, perhaps recognize the North Star. Your understanding of planetary movements might be limited to what was inherited from ancient texts, often incomplete or poorly understood. Calculating the exact time of day or night, determining your latitude, or predicting celestial events was an incredibly complex task, relying on rudimentary instruments or imprecise methods. Astronomical knowledge, while valued, was often intertwined with astrology, and lacked the precision needed for serious scientific inquiry or practical applications, like long-distance navigation. Far away, in the Arabic-speaking world, a different kind of celestial observation was taking place. Scholars had not only preserved the astronomical knowledge of the Greeks, particularly Ptolemy's Almagest, but had also rigorously critiqued, corrected, and vastly expanded upon it. They established major observatories in cities like Baghdad, Maraga, and Cairo, equipped with instruments of unprecedented size and precision. They believed that accurate observation was crucial for understanding the cosmos and for practical purposes like determining the correct time for daily prayers or finding the direction of Mecca. One of the most remarkable inventions to emerge from this vibrant astronomical tradition was the astrolabe. While its origins can be traced back to ancient Greece, Arabic scholars refined it, perfected its construction, and vastly expanded its uses. The astrolabe was in essence a complex analog computer capable of solving numerous astronomical problems. It was a portable, beautiful instrument, often crafted from brass. Featuring intricate engravings and movable parts, picture an astrolabe in your hand. Typically consists of a circular base plate called the mater, which holds several interchangeable plates or tympans, each engraved with a projection of the celestial sphere for a specific latitude. On top of these plates rests the rete, a skeletal star map showing the positions of the brightest stars. A movable rule or alidada with sights is attached to the back, allowing an observer to measure the altitude of celestial objects. With this single instrument, an astronomer could tell the time during the day or night by observing the sun or stars, determine the time of sunrise or sunset, find the direction of Mecca, calculate the altitude of celestial bodies, determine the latitude of the observer, solve various trigonometric problems related to celestial mechanics, predict the positions of planets and stars. Arabic astronomers like al-Battani, 9th-10th century, whose works were later translated into Latin, produced incredibly precise observations and developed new trigonometric functions to aid their calculations. They compiled comprehensive astronomical tables, known as zijes, which contained data on the movements of the sun, moon, and planets, as well as star catalogs. These tables were far more accurate than anything available in Europe at the time. Scholars like al-Tusi and Ibn al-Shatir later critically analyzed Ptolemy's models, making significant improvements that, unknown to them, prefigured some aspects of Copernicus's later heliocentric model. Transmission of this advanced astronomical knowledge and instrumentation to Europe was, again, primarily through Spain and Sicily. European scholars traveling to these regions encountered the astrolabe and the Arabic astronomical texts. Gerard of Cremona, the prolific translator in Toledo, translated al-Zarqali's work on the astrolabe and al-Battani's Zij, bringing these crucial tools and data to the Latin West. Jewish scholars like Abraham Bar Hia in Spain also played a vital role in transmitting astrolabe knowledge. The astrolabe quickly became a symbol of astronomical learning in Europe. Its elegance and utility were undeniable. European instrument makers began to craft their own astrolabes, following Arabic designs and instructions. Universities, particularly those with a focus on natural philosophy and medicine, started incorporating the study of the astrolabe into their curricula. Students learned how to use this intricate device to understand celestial mechanics, solve practical problems related to timekeeping, and even for navigation, though long-distance sea navigation with an astrolabe was still challenging. The influx of Arabic astronomical texts, including the Zij tables, provided European astronomers with far more accurate data and sophisticated mathematical methods for predicting celestial events. This led to a significant improvement in astronomical understanding in Europe, moving beyond mere contemplation to more rigorous observation and calculation. The astrolabe was not just a tool, it was a teaching aid, a research instrument, and a catalyst for further astronomical inquiry. It opened up new possibilities for understanding the cosmos, and provided practical skills that were invaluable for a society increasingly interested in exploration and accurate timekeeping. This fusion of Arabic observational precision and instrumental innovation significantly propelled European astronomy forward, paving the way for later monumental discoveries. Number 3. Experimental method and optics. Picture the traditional approach to understanding the natural world in medieval Europe. For many centuries, philosophical and scientific inquiry was heavily based on the authority of ancient texts, primarily Aristotle. To understand how the eye saw, for example, a scholar might consult Aristotle's ideas or Ptolemy's theories, which suggested that the eye emitted rays that touched objects, allowing for vision. Knowledge was often acquired through logical deduction from established principles, rather than through direct observation or experimentation. Questions were settled by appealing to authority, not by empirical testing. In the Arabic-speaking world, a different intellectual current was gaining strength. While respecting the ancients, many scholars began to emphasize the importance of observation, experimentation, and critical analysis. They questioned assumptions and sought to verify theories through repeatable procedures. This was a significant shift towards a more empirical approach to understanding nature. One of the most extraordinary figures embodying this new approach was Ibn al-Haytham, known in the West as Al-Hizn. Born in Basra in 965 CE, he spent much of his life in Cairo. His most famous work, Kitab al-Manazir, or Book of Optics, was a monumental 7-volume treatise that revolutionized the understanding of light and vision. It was not just a collection of theories. It was a meticulously documented record of experiments and mathematical proofs. Ibn al-Haytham fundamentally challenged the prevailing theories of vision. He rigorously demonstrated that light travels from objects to the eye, rather than the eye emitting rays. He did this through a series of ingenious experiments. He used a dark room, what he called a camera obscura, to show how images are formed. He observed how light passed through small openings, forming inverted images on the opposite wall, demonstrating that light travels in straight lines and that the image formation was a physical process occurring outside the eye. He also conducted detailed studies of reflection and refraction. He used polished mirrors of various shapes, spherical, parabolic, cylindrical, to study how light bounces off surfaces at different angles. He also immersed objects partially in water and observed how their appearance changed. Studying the bending of light as it passed from one medium to another, his experiments were systematic. He varied conditions, measured outcomes, and used mathematical reasoning to support his conclusions. He explored the anatomy of the eye, relating its structure to the process of vision, and discussing how light travels through its different parts to form an image on the retina. His rigor was remarkable, combining theoretical insight with careful practical investigation. Ibn al-Haytham's work went beyond mere description. It was a profound example of the scientific method in action. He formulated hypotheses, designed experiments to test them, observed the results, and then used mathematical and logical reasoning to draw conclusions. He emphasized that theories must be supported by empirical evidence, not just by philosophical speculation or ancient authority. This was a crucial step towards modern scientific inquiry. The transmission of Kitab al-Manazir to Europe was, once again, through Latin translation. 12th century translation, likely from Arabic, made the Book of Optics available to European scholars. It was eagerly studied and debated in the emerging universities. Its influence was immediate and long-lasting. European thinkers like Roger Bacon, a Franciscan friar and scholar at Oxford in the 13th century, were profoundly influenced by Ibn al-Haytham. Bacon, often credited with advocating for experimental science, explicitly referenced al-Haytham in his own optical works, such as Opus Majus. Bacon's own studies on optics, including his work on lenses and mirrors, clearly built upon Ibn al-Haytham's foundations. Witello, a Polish friar and scholar, also wrote an influential treatise on optics, Perspectiva, in the late 13th century, which extensively drew upon and popularized Ibn al-Haytham's theories. The impact on European science education was multifaceted. The Book of Optics became a standard text for the study of light and vision in universities. It forced scholars to reconsider the very nature of light and how we perceive the world. More importantly, it provided a powerful example of how to conduct scientific inquiry. It demonstrated the value of observation, the necessity of controlled experiments, and the power of mathematical reasoning in understanding natural phenomena. This empiricist approach, exemplified by Ibn al-Haytham, slowly began to permeate other fields of study. It laid the groundwork for later advancements in optics, including the invention of eyeglasses, telescopes, and microscopes. Demonstrated a new, more rigorous way of doing science, moving away from pure deduction and towards a method grounded in observable reality and systematic testing, which was a fundamental lesson for all future scientists. Number 2. The canon of medicine and systematic medical education. Imagine visiting a doctor in early medieval Europe. Medical knowledge was often a blend of ancient Greek texts, often poorly preserved or understood folk remedies and superstitious practices. Hospitals were primarily places of charity for the poor and sick, not necessarily centers of advanced medical treatment or rigorous teaching. Surgical procedures were risky and rudimentary, and pharmacology was limited. Diagnosis was often based on observation without a deeper understanding of underlying pathology. There was no standardized medical curriculum, and advanced education was sporadic and unorganized. In the Arabic-speaking world, medicine flourished into a highly sophisticated science, driven by a respect for knowledge, a vast pharmaceutical industry, and the establishment of dedicated hospitals. Arabic physicians not only preserved Greek medical knowledge from figures like Galen and Hippocrates, but also rigorously critiqued it, expanded upon, and systematized it. They emphasized observation, clinical experience, and systematic treatment protocols. The most influential figure in this medical revolution was Abu Ali al-Husayn ibn Sina, known in the West as Avicenna. Born near Bukhara in Central Asia in 980 CE, Ibn Sina was a true polymath, but his monumental contribution to medicine was al-Qanon fi al-Tib, or the Canon of Medicine. This encyclopedic work was not just a collection of existing knowledge. It was a brilliantly organized, comprehensive medical textbook that synthesized centuries of medical learning with his own observations. An expicture, the scope of the canon. It was divided into 5 books covering general principles of medicine, anatomy, and physiology. Theoria Medica, detailing thousands of drugs and their properties, based on both ancient texts and new Arabic discoveries. Specific diseases, organized by body part, describing symptoms, diagnosis, and treatment. General diseases affecting the whole body, such as fevers and poisons. Compounded drugs and methods of preparing them. Ibn Sina introduced concepts like contagious diseases, outlined clinical experimentation, and discussed surgical techniques. He emphasized the importance of diet and hygiene in maintaining health. His approach was systematic, logical, and incredibly thorough. It became a blueprint for organized medical knowledge. Simultaneously, the Arabic world developed sophisticated hospital systems. The first major hospital in the Islamic world was established in Baghdad in the 9th century. These hospitals, unlike their European counterparts, were not just places for the sick, but also centers for medical education and research. They often included lecture halls, libraries, pharmacies, and even dissection rooms. They had separate wards for different types of illnesses, e.g., surgical, internal, mental health, and both male and female patients were treated. Physicians gained practical experience by observing and treating patients, often in structured rounds with senior doctors. This was the earliest form of clinical instruction. Al-Razi, known as Razes, a Persian physician in the 9th–10th centuries, wrote extensively on smallpox and measles, detailing his clinical observations and differential diagnosis, emphasizing the importance of direct patient experience. Transmission of this advanced medical knowledge to Europe was again facilitated by translations. Gerard of Cremona's translation of the Canon of Medicine into Latin in the 12th century was a watershed moment. It quickly became the standard medical textbook in European universities, sometimes even into the 17th century. Other influential Arabic medical works, including those by Al-Razi and Ibn Rushd, Averroes, were also translated and studied. The impact on European science education was immense. Canon of Medicine provided European medical schools with an unprecedentedly comprehensive and organized curriculum. Students learned anatomy, pharmacology, clinical diagnosis, and therapeutic methods from a single authoritative text. Standardized medical training and elevated the status of the physician. The detailed descriptions of diseases, drugs, and treatments meant that European practitioners had access to far more sophisticated knowledge than before. New surgical instruments and techniques, often developed in the Arabic world, were introduced. The emphasis on clinical observation and a systematic approach to medicine, although not fully triplicated in European hospitals for centuries, provided a powerful model for future medical practice. The Arabic innovations in pharmacology, introducing new herbs and chemical compounds, significantly expanded the European apothecary's stock. The systematic approach to disease, diagnosis, and treatment laid down in texts like the Canon became the very framework upon which later European medical schools built their understanding, leading directly to the modern medical profession. Number 1. The rediscovery of Aristotle and the development of logic. Imagine the intellectual landscape of Europe in the early Middle Ages. While Aristotle's logical works, particularly the Categories and On Interpretation, were known in Latin translations, much of his vast output, especially his scientific treatises and metaphysical works, remained largely unknown or inaccessible. What was known was often through brief summaries or indirect references. European scholars, particularly in the nascent universities, relied on a limited philosophical framework, often struggling to reconcile ancient thought with theological doctrines. The rigorous intellectual tools needed for deep scientific inquiry, particularly systematic logic and natural philosophy, were underdeveloped. Meanwhile, in the Arabic-speaking world, Aristotle was revered as the first teacher. Arabic scholars had not only meticulously translated almost all of Aristotle's works into Arabic, but had also engaged with them profoundly. They wrote extensive commentaries, critically analyzed his ideas, and synthesized them with their own philosophical and scientific explorations. This was not a passive preservation. It was an active intellectual project of understanding, integrating, and often extending Aristotle's thought. Key figures in this intellectual endeavor included al-Farabi, 9th–10th century, who integrated Aristotelian logic and metaphysics with Islamic thought, and Ibn Sina, Avicenna, the famous physician who also wrote voluminously on philosophy. His Kitab al-Shifa, the Book of Healing, though not a medical text, was a massive philosophically that included sections on logic, physics, mathematics, and metaphysics, largely based on Aristotle. Ibn Sina's interpretations of Aristotle were incredibly influential. However, perhaps the most ably Arabic philosopher for Europe was Ibn Rushd, known in the West as Averroes. Born in Cordoba, Spain, in the 12th century, Averroes produced monumental commentaries on almost all of Aristotle's works. His commentaries were so detailed and inchable that he became known as the commentator in Europe. He sought to purify Aristotle's true meaning, often distinguishing it from Neoplatonic interpretations that had sometimes colored earlier Arabic understandings. He emphasized the power of human reason and the importance of logic as a tool for understanding the world. His work was characterized by a rigorous, analytical approach to philosophical and scientific problems. Transmission of these works to Europe was once again centered in Spain. As Toledo and other Spanish cities came under Christian rule, European scholars gained access to the vast libraries of Arabic works. Translations of Aristotle's complete works, often accompanied by the extensive commentaries of Averroes, began to flow into Latin. Michael Scott, a prominent translator in the 13th century, was particularly instrumental in translating Averroes' commentaries on Aristotle's physics, metaphysics, and De Anima, on the soul. These translations were immensely influential. The impact on European science education was revolutionary. Aristotle, through his Arabic interpreters, became the backbone of the curriculum in the newly established European universities. His works on physics, meteorology, biology, and especially logic provided a comprehensive framework for natural philosophy. Students learned to think systematically, using logical deduction and argumentation. The university disputation, a formal debate where students argued for and against propositions, became a central pedagogical method directly drawing from the logical rigor found in Aristotelian and Arabic philosophical tradition. Averroes' commentaries, in particular, provoked intense intellectual ferment. His emphasis on the potential for human reason and his interpretation of Aristotle challenged existing theological frameworks and sparked heated debates within universities. However, even among those who disagreed with Averroes, his methods of logical analysis and his comprehensive understanding of Aristotle became indispensable. Scholars like Thomas Aquinas, while criticizing some of Averroes' conclusions, nevertheless adopted much of his Aristotelian framework and logical rigor. This reintroduction of Aristotle, coupled with the sophisticated logical analysis and critical engagement offered by Arabic commentators, provided European scholars with powerful new intellectual tools. It fostered a culture of rigorous debate, systematic inquiry, and the application of reason to understanding the natural world. It meant that natural philosophy, the precursor to modern science, could develop on a much firmer and more comprehensive logical foundation. The emphasis on logical coherence, clear definitions, and systematic argumentation, all hallmarks of Aristotle, as transmitted and interpreted by Arabic scholars, became integral to academic inquiry, shaping the minds of generations of European students.